So the next presenter is Matthew Koop from AWS. So he's a principal solution architect for compute and HPC at AWS. He draws on a broad set of experience in large-scale computing from both commercial and public sector to work with customers on their large-scale compute requirements on AWS. He holds a PhD from the Ohio State University. So just like Jitin, he's also an alumni of the MVAPICH group. Interestingly, very similar thing, what I indicated about Jitin, Matt was involved in the very initialization virtualization work in 2006. And if I remember correctly, that time the adapter was QDR or something like that. So he has contributed quite a lot to the MVAPICH II code base. If you would have looked at some of the UD support, hybrid RC UD support, XRC support, some of the reliability. So all those things are like Matt did when he was a PhD student. So he also has a big contribution to the code footprint, okay, of the MVAPICH II code base. So with this, let's welcome Matt. He will be talking about service options and hardware choices for HPC on AWS. So Matt, you can share your slides and get started.
Dr. Panda, I think he has to be panelist, so let me...
No, I think he was, right?
I think he dropped off. I have promoted Matt to be a
panelist. Okay. Yeah. Okay. Yeah, I think now.
All right, sorry about that. That was my fault. I realized since getting this new system, I hadn't shared my screen on Zoom, so okay. It was complaining, saying I needed to restart. So
okay. No problem.
All right. So hopefully you can see my my slides up top. Else.
Yes.
All right. Excellent. Well, thank you for that introduction, Dr. Panda. Excited to be here chatting with you all today. Enjoy working not only with everyone on Dr. Panda's team, but also the greater community as well. So. As he mentioned, I'm a principal solutions architect at AWS. Work very closely with our EFA team, which I'll speak about as well, which ends up being a transport available through MVAPICH II to AWS. So I have a few different things I wanted to cover today. I won't have as many sort of performance results as say Jitin went through, but I want to kind of go through a lot of the different services our customers use and how these interact and where you can use MVAPICH in these. So I'll start off with kind of the three core areas we normally think about in HPC: compute, networking, and storage, and then sort of finish with kind of the workflow parts of this. So how do you get started using this? How do our customers typically use HPC on AWS? So the first part, if you're not familiar with it, Amazon EC2 is Elastic Compute Cloud, which is really, virtual machines or bare metal hardware today on demand. Then I'll talk a little bit about Elastic Fabric Adapter, which is our high performance networking that generally is used for tightly coupled HPC jobs, as well as our storage offerings. So the first one is just kind of instances in general. So instances is what we call the different sizes of virtual machines. And each time I give this presentation, I have to sort of double check how many instances we have and make sure I update the slide. So when I checked this morning, I think we were at 407 in one of the regions I checked. So these include a variety of things, everything from sort of the general purpose Goldilocks sort of platform that works for a lot of workloads to things that are going to have a lot of memory or maybe a lot of IO capabilities. So lots of NVMe capability. Others with accelerators of various types, different levels of networking, everything up to 400 gigabit networking, bare metal as well as virtual machines. And then, a variety of processor choices. So I'll talk a little bit more about that later as well. this doesn't happen quite as often as it did in the past, but I think it's a good thing to cover, which is, I said virtual machine, which sometimes makes people think, I'm not sure what that means in terms of my performance. If you kind of look at what EC2 was when it first launched, so this is 2011 or prior, our systems looked a lot like this, where we had instances, a fairly thick hypervisor. It was based on Zen. And we reserved a certain number of cores to do sort of that back-end work. So our networking stack, any sort of privileged networking, your storage. So even the sort of virtual block devices we had went through that same level, as well as all of the management and monitoring. And over time, right, you'd like to avoid that sort of thing. So starting in 2012, we moved some of the networking out of that as well. So it went into hardware using SRIOV. And over time, right, we continued moving other elements out. So storage became a virtual function through a PCI device. To today, which we call our Nitro architecture, which is you effectively have about 100% of what the server is. If you're using a virtual machine at the fullest size, so you kind of have a full machine underneath, there's just a very thin hypervisor there, which we call our Nitro hypervisor. It was KVM based, but kind of think KVM based and take almost everything out of it. And everything else is done through these virtualized hardware devices here at the bottom. So it makes it easier for us to not only implement things as, if you want an actual bare metal system, we can, because there's all of the devices are completely virtualized at a hardware level, as well as it gives you very high performance, even if you're using a hypervisor, which is what the vast majority of our customers use today. So I recently, wrote a blog that just showed some of this. So I took a few, HPC applications as well as benchmarks here. The full details are at the link below. But I compared just one of our metal instances, so to basically the same instance size in a virtualized mode. These are the same cost. They're basically the same hardware, and you can see. We're within a percentage point of virtual to metal here. Which is really within kind of a noise level. I don't see a big difference. And for our customers, they just sort of enjoy the virtual machine aspect, and its easier deployment, generally faster as well. The other element I wanted to talk about in sort of this EC2 section is processor choice. So obviously we offer processors from Intel as well as AMD, but we had a lot of other customer requirements that would come in that didn't necessarily fit into an existing processor. And so a few years ago, AWS started on this process of developing our own processors based on the ARM technology. And so our first one we released a few years ago, which was called just Graviton, which worked for some customer use cases, but it wasn't quite powerful enough for a lot of them. But it allowed us to really work out all of the ecosystem and infrastructure to be able to provide a more powerful one when it came out. So we released the Graviton II recently, which is a 64-core Neoverse N1 based platform. Worked very closely with them. I'm not going to go through all the stats here. A lot of times you'll find, cloud providers will use vCPUs, and then you kind of have to divide by 2 to give you the number of physical cores. In this case, there is no simultaneous multi-threading or hyper-threading. So when we say 64 vCPUs on this platform, it truly is 64 cores. It's a single socket platform, so there's nothing related to NUMA that you'll see. Not either in terms of multiple sockets on the platform, or in sort of chiplet design or anything like that. It's a mesh across the entire thing, and you'll see very consistent memory latency and bandwidth from whichever core you're using to the memory subsystem, which is going to be eight channels of DDR4. The last part I wanted to talk about for EC2 is GPUs. So as I mentioned before, we have a number of different GPU types. The latest GPU technology is the NVIDIA A100s. So our P4D instances contain 8 of those per instance. And those instances then have 4 100 gigabit EFA networking connections to them. And we've put them in what we call ultra clusters, which means that we've co-located, at least 4,000 of these GPUs in a single sort of cluster, and we've also made them accessible to our FSX storage, which I'll talk about a little bit later. So what we've seen with customers is not only do they just want very fast communication between all of their GPU nodes, but they also want to have connection to their storage as well at very high throughput rates. So that's just one of the things we'll do. This isn't to say we can't do this in other cases. So a very common use case for other customers is to have low latency, and you can request something called a placement group, which will ensure that we place them topologically close enough to give you your full bandwidth you need. So that was a little bit about EC2. And the next part I want to talk about is Elastic Fabric Adapter, or EFA. So EFA is really the AWS sort of cloud way of doing high performance networking. And so it has all of the sort of aspects that you expect from one that you would be using for HPC, including an OS bypass layer, the ability to do GPU direct and RDMA. And we provide both an RDMA core interface, which is what MVAPICH II X AWS uses, as well as a libfabric core support, which allows support across a wide variety of MPIs as well as nickel. The thing that makes EFA special is that it has a completely different protocol under the hood, which we call Scalable Reliable Datagram, or SRD. So this natively understands the sort of cloud scale networking that we have and the many different paths we have through our networks, which allows us to better react to congestion and other things that may be in the network at the time. The part of doing this allows us to really have this as part of the entire network, so it's not sort of segregated between different nodes. So you could see we have nodes that are both sort of the IO nodes with heavy disk usage, as well as those that are maybe used for GPUs, as we talked about earlier in ultra clusters. But we do that across a number of different instance types as well. So the other part of Scalable Reliable Datagram is it makes some trade-offs that are a little bit unique compared to some other interconnects. We have reliable transfer, which is not unique, but what's different is it's not necessarily in order. So we don't make guarantees on in order transfer with SRD. If you're really interested, I posted the notice there to the IEEE Micro, that paper that describes this, but it allows us to make some other trade-offs as to where we provide sort of reliability and that ordering layer, which gives us some flexibility when we implement things like MPI, and MVAPICH has taken advantage of that as well. So here's kind of where the software stack is. As I mentioned, we provide an RDMA core interface, which is generally the verbs level interface. There's not a lot of implementation directly on that level. MVAPICH II is one of the few that makes direct use of that level. And that's for the primary reason of you have to take care of things such as packetization as well as that reordering. And so MVAPICH II does some unique things around how it handles those reordering for large messages, which is great. And I've also linked the paper there. For support for other libraries such as OpenMPI and Intel MPI, as well as Nickel, We support those through the libfabric interface. So libfabric is really providing that ordering level segmentation and other features that SRD doesn't provide itself natively. And then that layer is generally how we support other types of applications, for end customers. But you can certainly write directly to the RDMA core layer as MVAPICH does here. As I said before, there's a wide variety of instance types. So everything from the Graviton II processor that I was speaking about, which is one socket platform, 100 gig, to a storage dense platform with up to 600 or 60 terabytes of disk space, to a wide variety of x86 platforms here, including the recently released M6i, which is an Ice Lake platform, Cascade Lake, Sky Lake, so on. And then you can see the wide variety of accelerators from A100s, V100s, T4s, as well as AWS's custom ASIC, the Inferentia chip for machine learning inference. So, all right, so that's a little bit about EFA and kind of how we get the networking performance we do. I want to touch a little bit on FSX for Lustre, which is the storage platform that a lot of our customers use. So if you can use something like an object store like S3, I generally recommend that you use that. But for most HPC applications, we still see that people need to use sort of standard POSIX IO, where they can randomly move to different parts of the file and such. And so FSX for Lustre is a managed version of the Lustre that probably all of you know as an open source parallel file system. What it does is it provides a managed solution, which means that you don't have to worry about spinning it up and down or the care and feeding of what version it is. But also it allows you to spin these up and down through an API. So you can decide at a job level if you want to have a specific Lustre file system attached to it or not. And you'll pay only for the time that it's attached. The great part of that is you can scale it up with different amounts of capacity that you think you need. There's a variety of different throughput options, so you can provision it on, the slide says SSD, but we also have hard drive based options with different sort of throughput levels per sort of tier that you have. So if look, I don't need that much overall throughput and I just need the space, you can save money by provisioning one with lower throughput. So this is a feature that we have a lot of customers that use. It's very powerful because you can do these things through an API at sort of a job level if you're interested, or you can just keep it running for months like you might use a typical Lustre file system today. The part that makes it a little bit different than maybe the Lustre that you're used to is we made it more, I'd say, cloud friendly. So a lot of customers, like I said, would like to store things in object store because that's generally a very cheap as well as incredibly durable place to store your data. And so you can see in this case, if maybe somebody has a bucket, which is just kind of a grouping of these objects in S3, you see file 1, file 2, folder 1, folder 2, and you want to be able to use these on your instances on the right side through POSIX IO. You'd love to have this loaded into your FSX for Lustre file system. So what you can do with the FSX for Lustre system is you can say, link these things to my file system directly. So you can give it an import path and all of the metadata gets loaded in. And then depending on how you want it to work, they can then be either lazily loaded off of S3 when you actually access them, or we can fill them up at the beginning. So part here is we can also do other things like if I add a new file, say file 5, it can also be auto-populated in my FSX for Lustre file system. So if, say, you have new experimental data, or you want to add a new job file, you could just put it directly into S3, which is often convenient for a lot of our customers, and then it can then directly be accessible through your FSX for Lustre file system. Similarly, you're going to probably edit those files. You may make new files as you're doing your computation, and then it can push those things directly back when you're finished as well. So you can say, basically push all of these things back into my S3 bucket, and then you could just spin it down. So as I said before, since this is a totally API driven, completely service-based thing, if you only need to run this job for a few hours and you want to provision it with all SSDs and you want high throughput, you can, and then you spin it down when you're finished. And maybe if you have something else that doesn't need very much IO, just provision something that's less expensive with less throughput. So that's one of the cool things we see a number of customers use. I'll speak a little bit about AWS Parallel Cluster here. One of my colleagues, Angel, I believe, had a tutorial yesterday where he went a little bit deeper into AWS Parallel Cluster. So I'll touch a bit on it here. So AWS Parallel Cluster is a way to kind of set up all of that stuff that I was just speaking about for the first part of this presentation. So one configuration file, and it can go provision an entire Elastic HPC cluster. That's probably very familiar to many of us. So it will create like a login node, and that's where you can log in, submit jobs, compile things, and it has a scheduler already. It will also create a number of compute nodes. The cool part is it can be elastic. So if you're not using it, you can configure it so it will go down to no compute nodes. And similarly, you could say, go up to 500 compute nodes if I need it. Right, and we'll only scale it up when you need it and shut it down. You can also set up a shared file system, right? So it does all the SSH keys and everything else for you, as well as makes it easy to use DCV, which is a virtualization, remote virtualization platform that AWS has, where it can be web-based or it has native clients that can run on your desktop as well, that can do all the way up to multiple 4K screens. The great part is if you're running that server on a EC2 host, there's no additional charge beyond the cost of EC2 itself. So we have a lot of customers that use that. It's also very extensible. It's actually an open source project. So you can edit directly, or there are a number of configuration ways where you can change a base image, post-install script, interactively add different things. So if you want to add a specific version of MVAPICH 2 or a specific tuning, you can have those all automatically set up as well. And similarly, I normally show sort of this thing where shows you what the config file is, and it will show you that it just spins it up for you. I think I will skip that in the interest of time to keep us on track here, but I know my colleague did share, I believe, something along those lines before, so I won't be missing anything. Batch is the last one I wanted to talk about, which is a little bit more of a cloud native approach to doing your compute. In this case, right, rather than sort of logging into a head node and configuring your jobs and submitting, this one it really doesn't have any sort of infrastructure that's always running that you're paying for. It just is waiting for jobs that you submit. So once you submit a job, it will say what your requirements are, so how much memory it needs, if it needs a specific type. You submit it to a job queue, and then it will be executed on what we call a compute environment, which could be, a whole different set of resources you've defined, specific types. This one is really often used for a lot of loosely coupled jobs, but it also does, tightly coupled, so we can use, EFA as well across multiple nodes here. It is entirely container-based, so your job does need to be containerized, but it's a very interesting option for a number of customers. So with that, I went through all the elements here from kind of the compute side, where I showed the variety of instances available, sort of the great the sort of great variety, which allows you to sort of choose what's best for your application, rather than just trying to fit into the one that might look like sort of the HPC one you have on prem. Talked about EFA and the design choices there. FSX for Lustre, which is one of the storage options that allows people to sort of rethink how they've constructed their jobs. And then Parallel Cluster and Batch, which are two common ways to use this infrastructure. And I'd say if you want to go try it out, Parallel Cluster is a good way to go to start. So we're obviously hiring. So if you're interested in the stuff that I talked about and are interested in helping build these things, we're hiring in lots of different locations. There's a link there, but feel free to reach out to me as well. So I don't know how much time we have, but happy to answer questions as well.
Thank you, Matt. We have time for at least one or two questions. I think Hari has posted some questions on the Slack. Hari, do you want to ask directly?
All right, looks like I can see those there. So,
oh, okay, go ahead.
Yeah, so I'll repeat it for everyone who may not be seeing it. So Hari said EFA has support for IB verbs, right? And so yes, it does. When I was talking about RDMA core, those are the IB verbs, right? So you can do an IBV post send and things like that. And so he said, does IB verbs go directly to the kernel driver, or does it go over libfabric and then to the driver? No, it goes directly to the driver, or bypass, right? Depending on what the operation is. So libfabric itself, the libfabric provider is using the RDMA core interface. So you're not losing anything necessarily by doing it, right? It's more of it's easier for people to implement there. And over time, right, we try to add more of those optimizations there, but it's, you're not losing out on performance by not using it, I would say.
Okay.
There is another question from Sule, just posted.
All right, so is memory consistency the only main concern for building Graviton ARM process instances with one socket? Do you have any plan or released instance types that include 2 sockets of Graviton on each node? I will say, I can't get into, and I'm probably not the right person to answer the question as to exactly why there's only one socket on that platform. We don't have any published plans around a 2 socket instance at this time, but we're always interested in customer feedback. So if we have customer demand that says, look, we have to have 2 sockets, we'd absolutely take that into consideration as we move forward. So
okay, I think there was Angel, you have posted something. I believe this was for Jithin's, all right?
So this,
Yeah,
I see it there. It was for the CFD benchmarks, OpenFOAM, Fluent. We're using all the available nodes, cores in the node. Actually, I think that was from a previous talk.
Yeah,
though.
that was for Jithin's talk.
Okay,
Yeah.
all right. I was going to say I didn't show any Fluent numbers.
Okay. Are there any other questions from anybody in the audience?
I'll get on video. My internet was a little unstable, so I didn't want it on when I was presenting.
Okay.
So Matt, quick question if I may.
Yeah.
Go ahead.
There was a mention about like the OFI nickel, right? So I'm just wondering, like, was it actually the EFA change, or was it like more changes like the nickel algorithm, etc.?
So there's a nickel plugin, right? So there's an OFI nickel plugin which uses the libfabric as an underlying transport level, And so, are you saying what did it change?
Yeah,
Or
was it only the transport level changes, or was it more like, I mean, or did it also include, say, I mean, the nickel algorithm, like say algorithm level changes, etc. Right?
I can't confidently say. It's another team that works on it, but I could certainly look into that exactly what their
Yeah.
changes were. Obviously, we needed some changes within EFA's libfabric as well to do that. But
Cool. Thanks, Mike.
Okay. So thank you then again, Matt. We'll try to remain on schedule. So